evening all. Welcome to the fifth section of Fundamentals of Additive Manufacturing Technology. So today we will be discussing on the uh, two lectures which is liquid additive manufacturing and their methods. The numerical parts have already been discussed. We will be discussing today on the other liquid additive manufacturing process 1 and process 2. This first one we'll be discussing on the per factory, which consists of DMD, recoating system and curing, and second we will also little bit discussing some questions on uh, the other liquid based additive manufacturing technologies, which are auto straight e-dart, solid ground curing, microstereolithography, and robotic SLA. So we will be discussing some brief questions on this. Before I start this, we will be just going through one numerical which relates to this question. A single axis galvanometer with a range of plus minus 15 degree is used in a SLA process. The beam deflected from the galvanometer is passed through a flat field lens to keep the focal point at a distance of 500 mm on the flat top surface of the liquid vat. In order to obtain a constant velocity of the laser spot as 10 meter per second, determine the range of the galvanometer's angular velocity. So here we have to find out the range of galvanometer, like maximum angular velocity and minimum angular velocity, and here we have been given the velocity of the laser beam on the flat surface, and we have also been given the function of angular velocity and theta value is angle of incidence. So with the formula which we already know, VH is equal to F into omega H by cos square theta. So by converting, we will get omega H is equal to VH cos square theta by F. Now we know VH is equal to 10 meter per second. So 10 by 0.5. This is 500 mm, which is 0.5. Now into cos square theta. This becomes 100 cos square theta. Now we have theta plus minus 15 degree, theta minus 15 degree. So putting this value, we will obtain WH maximum is equal to, putting plus 15 degree, we get 100, and WH minimum we get 100 into 0.933, which becomes 93.3. Okay, so this was the first question. Moving on to the main, this was some doubt in a previous class, so I just cleared it. So moving on to the next question, which is the topic of discussion, the different types of liquid additive manufacturing process. So what are the correct steps followed in a recoating cycle in per factory of photopolymerization based liquid additive manufacturing? So the liquid additive manufacturing based liquid additive manufacturing for a factory, it offers a coating cycle. This consists of certain steps. So if anyone is anyone aware of the option, you can just type in the chat box if anyone knows about the proper sequence. Okay, yes, B is the correct option. So as we know, it is the photopolymerization, per factory is the photopolymerization based additive manufacturing with the best cost to performance ratio, and it has various steps, which is exposure, then peeling, weighting, leveling. This is the recoating cycle. So and the per factory, it has various key features which have, like, they have reduced cycle time, they minimize the need for support structures, there are no lasers, and the mirror lifetime has a 2200 hours. And Apart from it, it also has a the exposure, which is it is done by Volex curing method. Okay, and the digital micro DMD, the digital micro mirror device, it is a crucial feature of per factory method. This is a binary light modulator. It consists of rectangular array of square micromirrors, and the major thing is when these DMD are powered on, the micromirrors can be individually addressed and rotated into either one of their two fixed operating systems. Okay, so moving on to the next question. Which of the following are advantages of solid ground curing? Solid ground curing method. If anyone has the idea about the answer, you can please type or unmute yourself and speak. Okay. This may be multiple. So one more option or two more options may be correct. Okay. So the correct options are A and B. So solid ground, the other C and D options, they are the advantages for the auto-straight EDAT method. Auto-straight EDAT method, which is also another photopolymerization based liquid AM. So first we'll discuss about the solid ground curing method. So the solid ground curing method, as we know, the principle is very similar to SLA. That is, when a light of appropriate wavelength falls on liquid photopolymer, the energy absorbed causes polymerization. And the photopolymer, which is polymerized, it will be in solid state. So here, this is the correct option. These two are advantages of. Now, apart from these two advantages, solid ground curing also it allows production like fabrication of many large parts and the support production of very large parts. Okay. So next is, sorry for the interruption. Milling and other advantages, milling step ensures flatness for subsequent layer and Z accuracy. So Z accuracy is very important. So we'll move on to the next question. So how is the solid ground curing similar to SLA? So here I will just mention about the steps when a light of photomolymer wavelength, this I already mentioned now, when a light of photopolymer wavelength, I am writing wavelength. The energy absorbed causes polymerization. So this principle is similar to SLA, and this is very important as this is the basic principle. Principle similar to SLA process. So what happens is when this flood of light is point against the pointed laser, this phenomena is similar to SLA, and this associated change, the flood which is made to pass through the optical mask, this mask is the negative of the region to be polymerized. Subsequently, the regions of liquid polymer where light falls become solid. And then the remaining liquid can be drained and its place is filled by liquid mask. So this SGC is completely similar with respect to SLA, and there are various steps involved, like creation of photomask, resin recoating, photomask placed, UV lamp is then turned on, removal of undercure liquid, wax recoating, phase milling, and final curing of UV lamp. These are the entire processes involved in SGC. And the major limitation of SGC is it creates a lot of waste of wax. That is why sometimes it is not used. Uh, it is not preferred because of this. Okay, moving on to the next question. Okay, which of these statements are correct for solid ground curing method? Okay, the solid ground curing method, the uh, first and last option, option A and option D are correct. In the first option, yes, in the solid ground curing method, no post cure is required as the polymerization is complete in the machine itself. Also, the milling step ensures flatness for subsequent layer and Z accuracy. Okay, but option B and C, dewaxing is time consuming, which I already said, and it creates a large amount of wax. So these are the disadvantages of solid ground curing method. That is, the dewaxing is very time consuming. It creates a lot of waste of wax, and also some other disadvantages are like building time. This depends on only the height of the part and not its volume. Rather, we should always consider the volume for the building time, because it controls the overall aspect of the our specimen. Also, this solid ground curing method, it has two cycles. That is, and it has two cycles and many subsystems like masking, polymer spreading, polymer cleaning, wax spreading, wax cooling, and etc. So it is less reliable, and this requires a very full-time operator attention. Disadvantages. These are the disadvantages of SGC, and this is very crucial while selecting any process. This contains many subsystems, thus requires complete operator attention. Okay. Moving on to the next question. This question will be covering a lot of methods altogether, which we will be discussing. The following problems occur in which method? Non-uniformities with the refractive index of the resin are difficult to control and monitor. Distance is limited, and in turn this limits the size of the part that can be made by this method. Unwanted resins may be formed along the path of either laser beams. So these problems occur in which method? Rapid freezing prototyping, two laser beam system, solid ground curing, microstereolithography. Okay, so the correct option is two laser beam system. So two laser beam system. This is a system which is not similar. This is quite different to SLA. This and this in the two laser system, what happens is two lasers are focused to interact at a particular point in the vat, and that is why it is also called as two-step photopolymerization. So it is assumed here in this system that so I'll be explaining on the two laser beam system. So here what happens is, this is, suppose this is the laser. Okay, and here suppose we have kept the sample. So this is the two photon polymerization. Now this is the visible laser and this is the IR laser. So what happens is when one laser excites molecules all along its path in the vat, then most of these molecules will return back to their unexcited state after a short time. Those also in the path of these second laser will be further excited to initiate the polymerization process. So on this basis, the resin cures at the point of intersection. This is the point of intersection of the two laser beams, while the rest, which are lying along either of the two paths, will remain liquid. So there are three major problems associated in the two laser beam process. These are, first is the that is the it is difficult that each laser beam undergoes numerous refraction. Each laser beam undergoes numerous refraction. What happens because of this is that as they move from the source in air through the liquid region, these there are various non-uniformity in the refractive index, and these are difficult to control and monitor because there are like various change in temperature and non-uniformities. This is the major um, due to which there are various non-uniformities. Second problem is now two laser beams moving at high speed be focused to a very small and accurate point of intersection. So when this distance is limited, this in turn limits the when laser beams move at a very high speed, they undergo numerous refraction. That is subsequently distance is limited and this in turn limits the size of the part that can be made by this method. Now the last one is unwanted resins are formed along the path of either laser beam. So these are the three major problems associated with two laser beam system. So the major issue is the cured resin, which because of all these unwanted resins non-uniformities, they may create further problems to the rest of the process. So moving on to the next method, this is solid ground curing, which we already discussed. Next is we will discuss on microstereolithography and rapid freezing prototyping. So microstereolithography, where we get very accurate parts and the focus point of the laser beam, this remains fixed. But the main disadvantage is it is very slow as compared to these other processes like two, two laser beam process or rapid freeze prototyping. And here So here we are majorly discussing on all the disadvantages of the processes. Now SGC we already discussed about the limitations, which is that is it gives amount the major disadvantage, it gives a lot amount of large amount of wax is produced, right? And these are the disadvantages for two laser beam photo process, and this is microstereolithography major disadvantages, very slow as compared to other processes. And next is rapid freezing prototyping. Disadvantages. Here we need to create or deposit the to produce overhanging or undercut feature. A support material is deposited in the required region of the layer. But the major trick is the support material is in step 10 eutectic sugar solution. So the rapid freezing prototyping, this like as we discussed the other photopolymerization based techniques, these generate various substances, like some generate smoke, some generate dust, some generate some chemicals which are harmful to human health. So, uh, with innovation to this, the rapid freezing prototyping was developed. But here, like the three-dimensional parts, these were, yeah, support material is dipped in like sugar solution as per my knowledge, but I'm not sure if do you have any prior idea on this? Like uh, it is as per me, this is the sugar solution which has formula C6H12O6 uh, dot H2O. Okay. So the build material, it is of water. Okay. Yes. No, no, no. See here, the three-dimensional parts are made by freezing of water droplets. Okay. So, okay. Okay. So you are asking about the which of the specimen of which you are trying to make, right? That material. Okay, okay, okay. So in that way, no. I was saying that the earlier, what I am trying to say is the build material, it is of pure water. Okay. While the support material is eutectic sugar solution. But if I'm, if this is as per my knowledge, but why did you say like it is of saline water? I just want to know. Did you have any idea on this experimentally or anything? Hello. Okay. Okay. Mm-hmm. Okay, like if there are doubt, I'll surely go and check into this, because since you have mentioned saline water, that may be, or that it may be saline water also. I'm not sure on this, but as per my knowledge, it is a eutectic sugar solution. But still, I'll go and look into it. Sure. Thank you for the question. Ah, so the freezing prototyping, this method is like they can make three-dimensional ice parts of arbitrary geometry layer by layer by freezing of water droplets. So it consists of three systems, subsystem, freezing chamber, electronic control device, and was that's positioning subsystem. So what happens is there is a nozzle, valve, and elevator that is in the freezer. Then we have a switching valve which connects the pipe of the nozzle and the syringe, that is a reservoir. A stepper motor is there. So here a two material extrusion method is followed. That is, there is a continuous nozzle and there is a drop on demand nozzle. So the drop on demand nozzle, it provides the feeding pipe, and the continuous nozzle, it provides the continuous layer by layer deposition. So here, to produce overhanging or undercut features, a support material is deposited in the required region of the layer. And this is the freezing. So earlier we all discussed the photopolymerization based liquid additive manufacturing, but this RFP is a freezing based liquid air. Okay, so this was from my side. If there are any further doubts, we can discuss. Okay, yeah, sure. I'll just share the PDF, else it will be easy for all of us to understand. So I just want to know, like, is the assignment submission due date over for this week's lecture? Okay, okay. Okay. So is the slide now visible? Okay. Okay. Sorry. Okay, I'll explain like this. So EDART, it is a photopolymerization based liquidative manufacturing. So here we we have this. Let's say this is the glass window. Here we have the glass window. Okay, this is the Z axis. Now what happens is laser. I'm just trying to make a 3D drawing, but still I may not be perfect. So just imagine a laser source coming from here and dropping into this point. Okay, this is the laser source. These are the y-axis. This is the x-axis movement. So now here we see the setup of this laser system. It is found, this laser system, it is found under the resin tank. This is the resin tank. The laser beam is directed into the resin, which is this is a container with a clear bottom plate. This is the container with the clear bottom plate. Now this system uses an acrylic resin. Okay. So here the model is formed by liquid resin, which is then cured by the laser light beamed. This laser light is coming from this resin chamber. Now this platform or modeling base is raised upward. This base, this is the base. This is raised each time a layer is completed. Now so here, what is the like benefits is it is a top down. This is a top down build strategy, as you must be seeing. So advantage is here. The advantage is beam correction is not required. So again I will explain this setup of this is the laser system. Okay. So this is found under the resin tank. This is the resin tank. Okay. The laser beam is now directed into the resin, which is in a container. This is a clear bottom plate. Now from upwards a laser beam is directed, which is a clear bottom plate, and this system uses I think acrylic resin to produce models. Now this model is formed by liquid resin, which is cured by this laser beam light below the resin chamber. Now here curing is done, and the platform or modeling, this modeling or platform, this is raised. This goes, this movement is the occurs. This is raised upwards each time a layer is completed. So this is the principle. That is why it is a top down building strategy, and here we do not need to uh, correct the beam, but yes. See, on here actually I'm not able to project this from here. From here, uh, uh, from here a laser is directed onto this plate, which goes like this. Like this, see upwards here, some projection like this is there. Something is there, okay. This thing is, you can also, if you have the image in your lecture, you can open that and you will see from this is the projection, okay. From here the laser is directed onto this, but when it is directed, it goes through this clear glass chamber. Glass window is there. This is the glass window, and this will be the movement up and down. This is the laser correction spot. Is it clear? Okay. Any more doubts? So, what I will suggest is uh, this uh, this uh, this today's live session. I discussed the theory because the Friday's live session, the numericals were discussed. So, so that there is no overlapping, we have like tried to go according to the first 10 questions. Like more, you have assignment questions 20 around approximately. So mostly we will be doing this. Like most first 10 questions will be similar concepts will be discussed by the in the Friday's live session, and the next one we will be doing it. I will be doing it. So any more further doubts? So I just want to know any further expectations, like any further expectations, how we can improve these sessions, or any further topics where clarity or something is required. We can always ask. I can we can prepare accordingly for the next session. Yes. Okay. Mm-hmm. Mm-hmm. Okay. So, yeah. So, yeah. That is true. Like, just. Uh-huh. Mm, okay. Uh, See, this is a thin layer of gas, oxygen, hydrogen, argon, helium. Are you talking about question number 17? So it is in the perfectory, which M lecture M03L04. If you will go, okay. So there we have discussed some perfectory photopolymerization based liquid additive manufacturing method, okay, where we discussed also the recoating cycle. So here it is asking which gas is used. So when you go to that, suppose no, that is wrong. See, argon is wrong for that thing. I can assure you. So okay, what you will do is when those perfectory, it is asking for this envision text perfectory, okay. So here when you will a image will be given and in that slides, okay. So usually in those envision tech perfectory we use Oxygen. Okay. So I said you the answer itself, it's oxygen. But still, if you go and refer to that slides, you will get the details. Okay. But argon is the wrong answer. Okay, these are like, what else? These are things you need to remember. We can't do anything on this. Yes, this will be taking time. I agree with you that because this is quite, this contains many processes and it will be difficult until unless you see the equipment working. Yeah. Any further doubts? So this is why it is this Envision Tech is like this perfect photopolymerization based additive manufacturing. It was invented by this some person who was from that company Envision Tech Germany. So that is why the perfectly Envision Tech it is written. So if there are no further doubts, we'll end the session. Yeah, thank you.